Okay, so this is sort of the chart I suggested for last time. I really do recommend you try to find these, try to derive these all yourself. See, and that really just helps you learn it. The more times you do this, the more comfortable you'll get with the concepts, the better you'll understand them, I think, and the more easily these things will stick in your brain. And practice makes perfect on this stuff. Okay, but I've got this out here because I want to show you what happens, or why we have this sort of strange cross-directional similarity. So you'll notice, I think, that resistors in series and capacitors in parallel seem to follow the same rules, right? Because for both cases, you just add the numbers up, okay? And conversely, you notice that capacitors in series and resistors in parallel seem to follow the same rule, okay? So you just add up reciprocals, and that's the reciprocal of your overall equivalent capacitance or resistance. Okay, so you're wondering why that is. Does this tell us something deep and meaningful about capacitors and resistors? Actually, no. It's a very simple. There's a very simple reason for that, and that is if we write. Just erase this down here. It's surprisingly. It seems surprisingly dull when you realize what the real reason actually is. But the reason actually is, I'm just carving out a little space here, is if you look at Ohm's law for resistors, V equals IR, and you look at the capacitor law, which is Q equals CV. I don't know why this isn't named after somebody. Maybe they should call it Faraday's law or something. I don't know. So you look at these two, look at where voltage is in each of them. And you notice here voltage is on the left by itself, and then we get current by multiplying, we take current multiplied by resistance to get voltage. Whereas here, voltage is on the side with capacitance. So the way to look at this really is that you can look at it as R behaves like, let me write this a little more space, R acts like, and I'm putting that in quotes because it's a very loose relationship, but oh, come on. Jeez, come on, seriously? There we go. R acts like 1 over C, okay? So, and when you put it like that, it becomes more obvious. So imagine we took, instead of talking about resistance, we talked about conductance, okay? So what we're going to do here is take a quantity called, we're going to call it conductance, and in fact I'm just going to give it a letter, capital K, okay? And I hope this doesn't seem too weird the way I'm doing this, but I'm going to talk about a quantity called, let me just, okay, so I'm going to define, where's the color? There we go. Okay, define conductance. Okay, K equals 1 over R. So then Ohm's law becomes I equals KV. Okay, and then you'll notice that Ohm's law, our new conductance-based Ohm's law, I'm spelling conductance with a K, so it's not capacitance, okay, looks like Q equals CV, right? So we find current by multiplying conductance times voltage. We find charge stored by multiplying capacitance times voltage, okay? And then when you look at in terms of conductance, then conductance is 1 over R. So what you get is 1 over the conductance, if you're doing series resistors, 1 over the combined, or the net, equivalent conductance is 1 over the conductance of 1 plus 1 over the conductance of 2. And then looking down here at parallel, well, I haven't left myself enough space, but I think you can see where this goes for resistors in parallel, which is that your conductance then just adds directly. So conductance 1, 2 equals conductance of 1 plus conductance of 2. Now, this is just this is an equivalent way to do it, and in fact, we could do it this way. All the math would come out right. We'd have to, use our results a little differently, but it would all work. And then you'd see that in parallel, conductance and capacitance obey the same rules, and in series, conductance and capacitance also obey the same rules. So the only reason why resistors and capacitors seem to obey different rules is because we set up the math differently for them. Because we usually talk about resistance. So this is the form of Ohm's law we use, and it's a different, you might say it's like a different structure, it's a different setup mathematically, algebraically, than the capacitor equation. And that's why we have to use different rules. That's why the rules switch. But if we use conductance, then it would all be the same thing. And in fact, some people do use conductance. They don't spell it with a C. They don't spell it with a K. And I don't know what variable they use, because, C would obviously be a problem. But they do have, people do use conductance, and conductance comes in units of mhos, which you'll notice is ohm spelled backwards, and you write mho like that, which is an upside down ohm symbol. So kind of cute. Not really anything you're going to have to use, but it's good. It's good to, the concept is useful for explaining why we have these different rules for resistors than we do for capacitors. And this is also why I like writing the series capacitor rule and the parallel resistor rule like this, because this makes it more clear what the structure is. It makes it more clear the relationship. And it also, as I've said before, makes it more clear what to do if you have more than two components in series or in parallel. Because it's pretty obvious looking at this that if you add more than two resistors in parallel, if you have like 5 resistors in parallel, you just keep adding, plus 1 over R3, plus 1 over R4, etc., etc. Whereas if you transform this into something like, so I'm going to take this and copy and paste and there we go. If you transform this into, that's good enough, into something like, you could transform this into R12 equals 1 over R1 plus 1 over R2, and then it's not too hard to figure out what to do if you have 3. But some people take it so far that they go like this, and they multiply top and bottom by R1 R2, and they get the R12 equals R1 R2 over R2 plus R1, and then this gets really confusing, because if you're going from this and you've got 3 resistors, R1, 2, 3, well, you might think that you just go, oh, okay, R1, R2, R3 over R1 plus R2 plus R3, right? But that's wrong. That's not what you do. And let me just lengthen my equal sign so I can draw a violent slash through it and show you it's not equal. If you have 3 resistors, what you actually end up getting is R1, R2, R3 over R1, R2 plus R2, R3 plus R1, R3. And that's just, this makes sense. You can go through and understand why this is true, and it's valid, but it's a lot harder in my mind to make sense of all this than it is to just understand this. This is just, to me, much easier to understand. So going back, there's our procedure, and yeah, I think that's it. So anyway, oh yeah, so last thing, okay, while I'm on this, is what's up with this capacitance being, okay, so charge, when you have capacitors in parallel or in series, why does the charge split in parallel and why does the charge stay the same? I'll do one more video on that.